This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover reduction potential. So first, we'll just establish what that is, and then we'll look at how we apply that to calculating the cell potential. Reduction potential measures how likely a substance is to be reduced. You'll be given reduction potentials in tables like what we have here, and they're always set up like this, where they have the reaction on the left where you see the species actually gaining the electron, and then on the right side of the arrow, you have the reduced version of that. And then you're given this value, this E naught, and whatever value that is. So here we have 0.77. That tells you how strongly that species will pull electrons to itself and become reduced. Notice that we do have the naught symbol, which means that we are at standard conditions whenever we get this value of 0.77. And standard conditions were talked about in the delta G video. So if you're not sure about those, go back and rewatch that video. The higher a reduction potential is, the more likely that species will be to pull electrons towards itself and get reduced. So iron 3+ is more likely to gain that one electron and become iron 2+ than lead 2+ is to gain those two electrons to become solid lead. And we know that because iron has a reduction potential of 0.77 and lead only has one of negative 0.13. So because iron's is higher, we know that it's more likely to get reduced than lead is. The other way you can view this is from the perspective of the species that's already reduced, and then it becomes how strongly will that species hold on to its electrons. So not how likely is that species to gain more electrons, but just hold on to the ones that it already has. So then if we take that perspective, we can compare something like lead solid and then react that with iron 3+ to see if iron 3+ can take electrons from solid lead. So when we compare those values, the way we want to think about this is iron 3+ is going to pull electrons with a power of 0.77, and then solid lead is going to hold on to electrons with a power of negative 0.13. Obviously, the 0.77 is stronger, so that means that the iron will successfully be able to pull electrons from solid lead. Conversely, if we did iron 2+ plus lead 2+, iron 2+ will hold on to those electrons with a value of 0.77, and then lead 2+ will try to pull those electrons with a value of negative 0.13. And then again, because 0.77 is larger, that means that iron 2+ will be able to resist the pull from lead 2+, and it's not going to lose those electrons. So then that reaction will not happen. One thing you want to make sure you're really clear on is that these numbers do not tell us anything about how likely the species on the right is to gain more electrons. It tells us how likely it is to hold on to its electrons that it already has, but not how likely it is to gain additional electrons. It tells us how likely the one on the left is to gain additional electrons, but for the one on the right, it only tells us how likely it is to hold on to the electrons it already has. We can take this idea and then prove it with some really simple experiments where we take a solid strip of metal, and then we dip that solid strip into a solution that has metal ions, and then we see what happens. So in the example on the left, we take a solid strip of metal and we put it in a solution that has aluminum ions. So now you want to think about, can the aluminum ions pull the electrons from that solid strip of metal? And you go through the same logic that we thought about earlier. So the solid strip of metal is holding on to electrons with a power of negative 0.13. And the aluminum ions are trying to gain electrons with a power of negative 1.66. So we can see that lead is holding on to its electrons with a higher value than what aluminum is able to try to pull those electrons with. So lead will successfully be able to retain its electrons, so we will have no reaction. For the image on the right, we're putting a solid strip of aluminum into a solution with lead ions. So the aluminum is trying to hold on to its electrons with a value of negative 1.66, and the lead is trying to gain electrons with a power of negative 0.13. So the lead is pulling those electrons with a stronger power than what aluminum is holding onto them with. So then we will have a transfer of electrons from solid aluminum to the lead ions. So lead will gain those electrons, and it will start to build up as solid lead. And it could build up maybe on the strip, or maybe it will just fall to the bottom of the beaker. But you will start to see the actual appearance of solid lead. And then the aluminum will lose electrons, and it will actually start to dissolve and go into solution. So over time, you will literally see that aluminum strip dissolve in that water, and then you'll see solid lead start to appear. And just in case this has already crossed your mind, to write out the full equation, you would have to approach this as though you're balancing a redox reaction, which we'll go over in the next part of this video. This brings us into the idea of the electromotive force. Electromotive force is just telling us how strongly those electrons are being transferred between those two species, and it depends on both the reduction potential of the metal that's losing electrons and the reduction potential of the ions that are gaining electrons. And we use this equation here at the bottom where we have E cell, and E cell is telling us how strongly those electrons are being transferred. And we get that by this equation, E cathode minus E anode. And E cathode is just the reduction potential of the species that gains electrons. And E anode is the reduction potential of the chemical that loses electrons. So for the example that we did previously in this video, that was lead taking electrons from aluminum. So we would do the reduction potential of lead minus the reduction potential of aluminum. So that would come out to be E cell equals negative 0.13 minus negative 1.66. And that gives us a total value of positive 1.53. And that unit is volts. Last thing we'll do is balance this redox reaction, both for practice balancing redox reactions, but also to point out that the number of moles that you end up with in your equation does not change how you use the equation that we just went over. So this equation is unchanged no matter how that balanced redox reaction looks. All you want to do is use the values that are given to you in a table of reduction potentials. So when you do a redox reaction, remember to first write your half reactions. And we know here that lead is gaining electrons, so that's your reduction half reaction. Your oxidation reaction is aluminum because that is losing electrons. After you write your half reactions, make sure that the number of electrons for both half reactions are equal, and we do that by multiplying half reactions by coefficients. So in the top reaction, we have 2 electrons, and the bottom we have 3 electrons, which means that the smallest number both of these go into would be 6. To get the top reaction to be 6 electrons, we need to multiply that by 3. To get the oxidation half reaction to 6 electrons, we need to multiply that by 2. Your reduction reaction becomes 3 lead plus 6 electrons, gives you 3 solid lead. Your oxidation reaction becomes 2 solid aluminum, turning into 2 aluminum 3 plus 6 electrons. Now you combine everything that's on the left and put that all on the left side of your final reaction. So that is 3 lead 2 plus 6 electrons plus 2 aluminum gives you 3 solid lead plus 2 aluminum 3 plus 6 electrons. And then the final thing you do is cancel out anything that shows up on both sides like you do with any equation. So we cross out our 6 electrons, and then what is remaining is your balanced redox reaction. So notice that we have 3 moles of lead and 2 moles of aluminum, but in your standard reactions, you only have 1 mole of each. But that does not change anything about this equation that we use below. These numbers are just telling us how strongly is each electron being transferred. So the total number of electrons does not affect these numbers at all. In a future video, we'll talk about how the number of moles will change some things, but this equation is not one of those things.